In this problem, we're going to look at the distribution of the weights of newborn children. We have some data from a hospital, and we're going to use that to figure out what we can expect in terms of weights for newborns. And we start off with the distribution is defined by the mean weight equals 2.9 kilograms, and the standard deviation equals 0.45. Oops, let's put it over here. 0.45 kilograms. And from this, we can get the shape of the bell curve, and we can then figure out the answers to these different questions. So the first question is the percentage of infants who weighed less than 2.1 kilogram. So let's see. So for question A, we want the percent of newborns who weigh less than 2.1 kilograms. And so to do that, we need to know what area of the normal curve lies to the left of 2.1 kilograms. So let's start a table here. Let's put weight here, weight, and then we're going to calculate a z-score, and then we can have let's calculate both the percent less than that weight and the percent more. So the percent less than and the percent greater than. And we'll be able to do some calculations that way. So the first weight is 2.1 kilograms, 2.1 kilograms. The z-score, we're going to use our formula. Z equals the raw score minus the mean divided by the standard deviation. That's the formula we're going to use. So let's put this into a table. Insert table. It says that looks good. So the z-score is going to be equals, and we're going to put open parentheses, and then E5 minus, now the mean weight is always going to be C4, so I'm going to put $C, $4, close parentheses, divide by the standard deviation, which is going to be $C, $5, and got a z-score of minus 1.788. Let's change that column to two decimals, home, number. Okay, and so we're going to use it to get the percent less than 2.1. We're going to use the equals norm s dist of the z-score. And so the z-score is going to be F5, close parentheses, and that gave us 0.03. This is a really light baby, which you would expect. It's almost 2 standard deviations below the norm. And the percentage greater than that weight, remember there's 100%, so we'll do 1 minus G5. Whoops, what happened there? We didn't put the equal sign in. Let's put the equal sign in. 1 less than minus G5. And let's change this column to 2 decimal points. And let's change this column to 2 decimal points. And so we can say for the first question, the percent of newborns who weigh less than 2.1 kilograms is Well, let's actually change this to the percentage. Let's go to percent, and we can add a few decimals. Use this one to add decimals. Over here, we can go to percent also and add a few decimals. Okay, so the percent of newborns who weigh less than 2.1 kilograms is going to be 3 point equals 3.77%. And so that's the first question here. Now on the second problem, we're supposed to calculate the percentile rank of a baby that weighs 4.2 kilograms. So let's write down percentile rank of 4.2 kilograms. And what is that going to equal? Now, so let's put down a 4.2 baby here. So that got added to the table and everything was recalculated automatically. So 4.2 kilograms is 2.8. That's a z-score, so that's a 99.81 percentile. So we will put 99.81%. That's a big baby. Oops, percent. Now let's see, let's label these things so we can tell what's going on. I'm going to insert another row, another column here. Right click, insert. Now I'm going to say that this was problem A, and I'll do enter. And since it's at the left of the table, it doesn't automatically make it join the table. If it did automatically join, I didn't want it to be a part of the table. There'd be a little box here that I could choose. This was for B, the percentile rank of a 4.2 kilogram baby. Now this one for C, we want to find the percentage of babies between 1.8 and 4 kilograms. So we want the percent between 1.8 and 4.0 kilograms. And remember the video said that in order to do that, we need to subtract the two percentages. So let's put a 1.8 kilogram baby here. And so that's a really light baby. And so that's 0.73%. Only 0.73% weigh less than that. And then the 4.0 kilogram, now that was how much my son weighed. In France, we always weigh babies in kilograms. That's 2.44 above, and so 99.27% is way less than a 4 kilogram baby. So what we're going to do is the percent between 1.8 kilograms and 9.8 kilograms, we're going to do the 99.27% minus 0.73%. So actually, why don't we write that out? That'll equal 99.27% minus 0.73%. And then we can actually calculate that here, and we'll put equals 99. Let's convert it. Let's see, 99.73 minus 0.73 equals 99. Let's see, let's add some decimal points to that. We can see what's happening. Do we have some text in there? Oh, you know what? Why is that not showing up? Let's get 2 decimal points there. Oh, that's 99.00. Why is that? What did we do here? 99. Oh, I did 99.73. It should have been 99.27. That was a mistake. So 99.27 minus 0.73 equals 98.54%. Let's put an equal sign at the end of this one so this looks a little better. Okay, so the percent between 1.8 and 9.0 kilograms is 99.27% minus 7.3% equals 98.54%. Almost all babies are between 4 and 1.8 and 4 kilograms. We can put that this was for C. This one was for C also. Now the next question is, I'll write it down here by where we can put it. The percent between 3.4 and 8.1 kilograms. Okay, so D is the percent between 3.4 kilograms and 4.1 kilograms. That equals, and we need to put that here, so 3.4 kilograms. That's in the 86th percentile, and 4.1 kilograms is a 99.62%. So that's going to equal, all right, equals, so it'll be 99.62, the percentile rank of the larger, minus the percentile rank of the smaller, which is 86.67. And that will equal, let's make these columns a little bigger so they don't overlap. That will equal 99.62 minus 86.67, 12.95%. So 12% of the babies lie between 3.4 and 4.1 kilograms. Okay, now the next question is E. So it says the weight that divides the distribution such that 1% of the babies are above it. Okay, so 1% of the babies. So we want the dividing line. We want the dividing score between bottom 99% and top 1% of babies. So what we need to do is we need to calculate, we're going to go from a percentile rank to a z-score. So let's make a new table here and start off with percentile rank, and we want the 99th percentile. It's the 90 percentile rank. So let's put in 0.99. Let's make this into a table too. Insert table, enter. Okay, and we want the z-score that corresponds to that. Z-score. And to get the z-score, the command that we're going to use is the norm S inverse. That's the norm S inverse. That goes from the percentile rank to the z-score of this percentile rank, F15. And so that gives us, says that a z-score of 2.33 will put us in the 99th percentile. So 99% of the babies will be below a z-score of 2.33 and 1% above. And so from that z-score, we need to go to the weight, which is the raw score. The raw score. And so the formula here is if we solve for x, we would get x equals the mean plus the z times the standard deviation, the standard deviation. And so we're going to still use the mean of 2.9 and 0.45. So the weight, the raw score is going, we'll use our Excel formula, equals, now the mean is C4, let's put a dollar sign in case we have to do another one of these, C4 plus the z-score, which is G15, and that's going to be times the standard deviation, which is at 0.45 there, the C5. $C $5, and that gives, oh look, that's in percentage. We don't want that to be in percentage. Let's change that to a number. So that equals 3.59 kilograms. So we can label this as being for question E. And so the answer to the E is a dividing weight. Let's say dividing weight between the bottom 90% and the top 1% of the babies equals 3.95%. And we type enter, and we've solved for E. Now the next one, F, what does F ask? F asks, beyond what weight of scores do the most extreme 5% of the scores lie? Okay, so we're looking for the most extreme scores. Now, extreme in statistics has a very specific meaning. It means far away from the mean, far away from the average. It can be far away on the high side or high away on the low side. So we need, so the most extreme 5%, that would be 2.5% on the low side and 2.5% on the high side. So here we want to find 2.5% of babies are below something, and 2.5% of babies are above something. So that would be the most extreme 5% would be the 2.5% heaviest and the 2.5% lightest. So the 2.5, the babies that are the highest 2.5%, we can say that that equals 1 minus 0.025, because that's the cutoff point there. So whoops, we don't need that place formula inside table. Okay. So we want the top 2.5%, that'd be the 97.5 percentile. And then we also want the bottom 2%, the 0.025 percentile rank. And that would give the bottom 2.5%. So the top 2.5% would have a z-score of 1.96 and a weight of 3.78 kilograms. And the bottom 2.5 would be below 2.02 kilograms. So 2.5% of babies are below 2.5 kilograms, and 2.5% of the babies are above 3.78 kilograms. So that's the 5% most extreme weights of babies for F. I'm going to say both those lines are for F. And now for G, so the 15,000 infants have been born at the hospital. So we've got 15,000 babies. How many weighed less than 3.5 kilograms? Oh, okay, so 15,000 babies, and what percentage weighed less than, or what's the total number that weighed less than 3.5 kilograms? Let's go back up here. This this is G here, and we want to find the percent less than 3.5 kilograms. That's the number, right? 3.5 kilograms. Okay, so 90.88% of the babies weighed less than 3.5 kilograms, but we've got 15,000. So we want 90.88% of 15,000 equals. Now, whenever we have of, that means multiply. So we want to, the number that would equal would be, let's do 0.9088 times 15,000. Let's not put the comma in there, 15,000. And that, oops, well, we need to put an equal sign in there, so that'll be an Excel formula. So equals 0.9088, that's our 90.88%, times, that's our of, and then there's 15,000 babies, and we press enter. That equals 13,632 babies have been born who weigh less than 3.5 kilograms. And so that's our answer to part G.